Good morning, students. The chapter that we'll discuss today is semiconductor. This is Shantini Datta. The topics that we'll discuss today: energy band of conductor, semiconductor and insulator. Why is semiconductor more preferred than conductor? Type of semiconductor: intrinsic semiconductor and extrinsic semiconductor. Type of extrinsic semiconductor: N-type semiconductor and P-type semiconductor. PN junction or diode, forward bias and reverse bias, rectification, half wave rectifier, full wave rectifier, and Zener Diode. In conductor, semiconductor and insulator, the energies are in the form of band. There are two bands, one valence band and another conduction band. Valence band, it is the wide range of energy possessed by valence electrons. Now, what are these valence electrons? Valence electrons are the bound electrons. Those electrons which are bound, those are known as valence electrons. So the wide energy possessed by these valence electrons are called valence band. Next, conduction band. Conduction band, it is the wide range of the energy possessed by the conductor electrons or the free electrons. So free electrons, the energy, the band energy or the range of energy contained by free electrons are known as conduction band. Obviously, the energy level of the valence band will be lower compared to the conduction band. Conduction band means it contains free electrons, that means it has more energy compared to the valence or the bound electrons. And the gap between it, there can be gap or there may not be any gap. There can be a situation where valence band and the conduction band are overlapping each other. So if there is a gap between a valence band and conduction band, that is known as forbidden energy gap. The region between the conduction band and the valence band is called a forbidden gap or forbidden energy gap. Now we'll discuss the energy band of the insulator, conductor and semiconductor. First, as you can see in the screen, there are two bands. One valence band which contains the bound electrons, another the conduction band which contains the free electrons. What happens in the case of insulator? The gap between the energy gap or the forbidden energy gap, this gap is a larger in insulator. It is about 6 to 9 electrovolt. The electrons require about 6 to 9 electrovolt of energy to jump from valence band to conduction band. In case of insulator, and if you can supply that amount of energy to the electron, about 6 to 9 electrovolt of energy to an electron, then it will jump to the conduction band from valence band. Now, if I heat a substance, an insulator in such an amount, what will happen actually? The structure will itself change. So that's why in insulator there are lack of free electrons. The electrons cannot jump from valence band to conduction band easily because the gap between it is large, is a huge gap between the valence band and the conduction band. Second case is of a conductors. Now over here you can see only one diagram is given, but there are two diagrams. There are two possibilities for conductors. Number one, as you can see in this diagram, it is given the valence band and the conduction band are overlapped each other. This is the first condition, where the valence band and the conduction band are not only there is no gap, but also they are overlapping each other. Next is that another case can be like that conduction band is partly filled and valence band is fully filled, but there is no gap, there is no overlapping also, and there is no gap. The valence band is fully filled and the conduction band is partly filled. Okay. Next is semiconductors. Now in semiconductor, what happened is that the gap between the valence band and the conduction band is there, but it is a very small amount. The energy is almost 1 electrovolt. So to jump from the valence band to conduction band, the electrons require a very small amount of energy, about 1 electrovolt of energy, to jump from valence band to conduction band. So the next topic is, why is semiconductor more preferred than conductor? In conductor, there is a huge amount of free electrons available. So why do we prefer semiconductor in creating any electronic devices? Why do we prefer semiconductor compared to conductors? Now in conductors, there is a free electrons and it can flow a huge amount of current. But the property that the semiconductor has is that you can make a semiconductor to behave as an insulator as well as conductor. So there are possibility that it can behave as a conductor, there is a possibility that it can behave as an insulator. So you can actually control the flow of a semiconductor, what you cannot do in the conductor. So that's why the semiconductor is preferred more. Next is type of semiconductors. There are two types of semiconductor. One is intrinsic semiconductor, which is also known as pure semiconductor, or it is said to be undoped semiconductor. So one is intrinsic semiconductor or pure semiconductor. Another is extrinsic semiconductor or impure semiconductor. Extrinsic semiconductor, there is again two types of extrinsic semiconductor. One is P type, another is N type. So the next topic is intrinsic semiconductor. Pure semiconductor, that is in which no impurity is mixed, is called intrinsic semiconductor. These intrinsic semiconductor behaves as an insulator when at the lowest temperature, that is the absolute temperature, the intrinsic semiconductor behaves as an insulator at 0 Kelvin. The electrical conductivity of a pure semiconductor depends upon the number of electrons excited from the valence band to conduction band, which is called the electrical conductivity. The number of free electrons per unit volume, that is the electron density, is equal to the number of the holes per unit volume, that is the hole density. So what happens is, in intrinsic semiconductor, it is a pure semiconductor. So if the silicon is there, the whole element is made up of the whole atom which are there is silicon only, or germanium, etc. So there are nothing other atoms are present, no other atom is present over there. So full intrinsic semiconductor is full pure semiconductor. First thing. Second, you can say that nothing impurities is, no impurity is doped or no impurities is mixed with it. So it is a pure semiconductor, and the number of electrons is equal to the number of holes, or you can say the hole density. The number of free electrons per unit volume is equal to the number of holes per unit volume. So hole density is equal to the electron density, or number of electrons is equal to number of holes. Next, in intrinsic semiconductor, it behaves as a insulator at the lowest possible temperature, that is the absolute temperature. At absolute temperature it behaves as a insulator. Now, what is the demerits of the semiconductor? First, number one, since it have very small number of charge carrier, thereby its conductivity is also low. So first demerit is it have a low conductivity. The conductivity is very negligible. Second is that it has equal number of electrons and equal number of holes. So it falls into a demerit that it has a equal number of, it cannot increase the number of electrons, no number of electrons cannot be increased. So whatever the electrons will come out, that only holes will be generated. As you can see in the diagram also given over here, that when the electrons are moving out, then only a space is creating, that is called hole. So electrons and holes are being equal number. If a one bond is from one covalent bond is broken, then only one electron will get out of that bond or become free electron, and then only a space can be created, which is called the hole. Right. Next is that in this case, in intrinsic semiconductor, you need to give heat energy or thermal energy to make the electrons come out from the covalent bond. So thermal energy is needed. So there are three demerits. Number one, it has a very low conductivity. Number two, thermal energy is required, or the energy is required to knock off the electrons from their bonds. And third is that it has a number of electrons and number of holes is equal. Extrinsic semiconductor. Extrinsic semiconductors are mostly used in semiconductor devices or electronic devices. Rather than using intrinsic semiconductor, we use extrinsic semiconductor. What is extrinsic semiconductor? When a semiconductor is doped with impurity, that is a extrinsic semiconductor. The addition of impurity to obtain a desirable property in the semiconductor is called doping, and the impurity is called dopant. Based on doping, the extrinsic semiconductor are divided into two types. One is N-type and another is P-type. N-type means when a semiconductor is doped with pentavalent, then it is a N-type. And if the semiconductor is doped with trivalent, then it is a P-type semiconductor. N-type semiconductor. Now, N-type semiconductor occurs when it is doped with pentavalent. So N comes with a pentavalent. When you are doping with pentavalent, the impurities that we are adding is pentavalent, then it is a N-type semiconductor. Second, what you have to remember over here is that the impurities that we add is always in a very small amount. If the impurities are in a larger amount, then we will say it is heavily doped. So the concentration also of the doping varies. It can be heavily doped or it can be lightly doped. Always the impurity which is added is always in a less amount. But if the concentration is more of the doping, then we can say it is a heavily doped. A n-type semiconductor is formed when a small quantity of pentavalent impurities is added. Now what happened in pentavalent means, for example, phosphorus, it has a 5 valence electrons, free electrons. So 4 of the electrons or 4 of the 5 electrons of the impurity or impure atom will participate in forming the covalent bond with the silicon or germanium. The 5th one is almost free. Okay, the energy level of these electrons lie very close to the bottom of the conduction band. These free electron has some certain amount of energy, and this energy is almost very much near to the conduction band. That's why it is also called a donor level. So n type means the impurity is pentavalent. It is a donor type. Okay, it almost have one free electron. 4 of the electrons participate in the covalent bond. Next is that since this type of semiconductor has excess of electrons than holes, so its majority carriers will be electrons and the minority carriers will be holes. As you can see in this diagram also is given, the excess phosphorus has been taken over here and the silicons have been beside it around this phosphorus. If one phosphorus is over here and so many of silicon is there, so impurity should always be in a smaller quantity, smaller amount, and phosphorus has 5 electrons which participate in the bonding with this all the silicon atoms, but one electron will be free, and these electrons has the energy level of these electrons is near the conduction band, just bottom level of the conduction band. The majority carrier of n type will be electron and the minority carrier will be holes. Next is that p-type semiconductor. A p-type semiconductor is formed when a small quantity of impurity such as aluminum or boron is added to a pure semiconductor. So we are adding a small quantity of impurity, a trivalent impurity. We are adding a trivalent impurity which has a valency 3. Okay. The 3 valence electrons of the impurity atom forms a covalent bond with the 3 neighboring semiconductors or the germanium or silicon, but one electron is lacking. One space will be there, one hole will be generated. Okay, thereby generating a hole in the bond. The energy level of these hole lie very close to the valence band, above the valence band, and it is called the acceptor level. Since in this type of semiconductor it has the excess of holes over electron, so the majority carrier for the p type will be holes and the minority carrier is the electron. So what you in total have to remember? First you have to remember the impurities. N type of semiconductors have pentavalent, p type has a trivalent. First. Second is that since it's pentavalent means 5 valency, 4 will participate with the silicon atom, only 1 will be free. So the majority carrier is electron over here and the minority carrier will be hole. Whereas for the p type, the majority carrier will be hole and the minority carrier will be electrons. Next is the energy of the energy level. The donor level lies very much close to the conduction band, and the acceptor level lies very much close to the valence band. So the next topic is the difference between the intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductor means it is a pure semiconductor. So there is no impurities are added, nothing is added. The full semiconductor is made up of, suppose it is made up of silicon, so the full is made up of silicon or germanium. In extrinsic semiconductor, if I add trivalent, then it becomes a p-type semiconductor. If I add pentavalent, it becomes a n-type semiconductor, and it is a impure semiconductor. So it is a pure semiconductor, it is an impure semiconductor. Depending on whatever we are doping, whether it's a trivalent or pentavalent, it can be p-type or n-type. Next is that number 2, in intrinsic semiconductor, the number of holes is equal to number of electrons. In case of extrinsic semiconductors, there are majority carrier and the minority carrier. We have already discussed about it. In case of p-type semiconductor, the majority carrier is the holes and the minority will be electrons. In case of n-type semiconductor, the number of free electrons will be more, so the majority carrier will be electrons and the minority carrier will be holes. Next is the Fermi level. So in the energy band diagram, where the energy lies, the maximum energy, the Fermi level lies. So for the intrinsic semiconductor, the Fermi level lies just in between the valence band and the conduction band. Whereas in the extrinsic semiconductor, if it is a p-type semiconductor means it has a majority carrier is holes. So holes means the vacant space that will be near the valence band. So the Fermi level or Fermi energy level will lie near the valence band for p-type, and for n-type it will be near the conduction band. Next, the majority carriers and the minority carrier, if I do a ratio for it, majority carrier versus minority carrier, the ratio will be 1 for the intrinsic semiconductor. For the extrinsic semiconductor, the ratio is never 1, because there is a majority means only there is a large number of electrons and large number of holes. They will never be equal. One will be in a larger amount, in another will be in less amount. In intrinsic semiconductor, actually there is nothing majority or minority, because number of electrons is equal to number of holes. Here you can see the over here you can say the ratio of the electrons and the holes are equal to 1. So the next topic is PN junction or diode. Now this is a very important topic. So what is a diode? When a p-type semiconductor and an n-type semiconductor are brought together and comes into a contact, it forms a PN junction or a diode. This is the theoretical information. Like if I take a p-type semiconductor, n-type semiconductor and join together, that forms the surface of the joining forms a PN junction. In other words, we can say that actually in practical what happens is that to make a PN junction we use a single crystal and we change the dopant. Next is that what is a diode? Now diode is a two-terminal electronic component. It has two terminals. So it's a two-terminal electronic component that conducts current in one direction. So this is a device which will allow the current to flow through only in one direction. An ideal diode will have zero resistance in one direction and infinite resistance in the reverse direction. That's why it allows the current to flow in one direction. So the ideal diode is that which will have zero resistance in one direction and about infinite resistance in the reverse direction. Next we'll study the mechanism or the working of the PN junction. Now the working is very simple if you just understand the concept. Okay, when we understand the working of PN junction, we are doing it
in the concept when there is no biasing, means the diode are not connected with the batteries, not neither forward bias nor reverse bias, nothing is there. So no biasing is there, just the mechanism inside the diode. We are just studying the mechanism inside the diode. Now what is it that what we have done, how we have created a p-n junction diode? By taking a p-type semiconductor and n-type semiconductor. P-type semiconductor is those semiconductor which has majority carriers are holes, and n-type semiconductors whose majority carriers are electrons. Now what happens over here when p and n-type come together is that these particles always have the tendency to diffuse from the higher concentration to the region of the lower concentration, right? So the diffuse always takes from the higher concentration to lower concentration. So from the p type, the majority is holes. The holes will try to go from p to n to the lower concentration. Okay, so higher concentration to lower concentration, p is moving, the holes are moving from the p to n, whereas the electrons are moving from the n to p, because the majority carriers of electrons are in n type. So n to e, the electrons are moving. Thereby when the holes and electrons are moving together, what will happen is that combination will happen. Due to the electron and hole combination, a thin layer will be formed across the junction. Okay, due to this recombination of electrons and holes, a thin layer will formed across the junction. And what will happen, this junction will have free of charge. There is no charge because the electrons and holes are combined together, and there is free, that layer is free of charge. This layer is called depletion region, and the thickness of this region is about 10 to the power minus 6 meter in few microns. The diameter of this the thickness of this depletion region is about few microns. So the next topic is potential barrier. Now, due to the migration of the electrons and the holes, the n region, the n type, becomes positive because the electrons are moving out from the n region. Thereby the n region becomes a positive, while the p region, where the holes are there, the the holes are moving out. Thereby it is becoming the positive charge is moving out, thereby it becomes the negative. This establish the electric field across the junction, which is directed from the n region to p region. So what is happening, from the n side the electrons are moving out, thereby it is becoming positive, and from the p side the electrons are entering as well as the holes are moving out, therefore the p region becoming the negative. Now since n becoming positive and p becoming negative, thereby a potential difference is there, thereby a electric field will be generated. This electric field across the junction will be directed from the n to p. Okay, due to this a potential barrier is come across, there becomes a potential barrier also, because the electric field also develop as well as a potential difference also develops. This potential barrier, what it does, it prevents the further diffusion of the carrier into the opposite region. So it stops the diffusion. It's once it becomes in a certain value, so it will stop or it will prevent the further diffusion of the carrier. The value of this potential barrier and the width of the depletion region depends on the semiconductor and also its concentration, doping concentration. So the next topic is forward bias and reverse bias. Now we know about the diode, that is the p-n junction. There is one p, another n. When the p is connected with the positive terminal and the n is connected to the negative terminal, then it is a forward bias. So when a battery is connected across the junction, with this the positive terminal is connected to the P side and the negative terminal is connected to N side, then the diode is said to be forward bias. Biasing means nothing but just putting a battery to it. So when P is connected to positive and N is negative, then it is a forward bias. Now, if the bias voltage, that is the battery what we are attaching it, the bias voltage is greater than the barrier potential, then the majority carriers move towards the junction and crosses it. Thereby, this causes the flow of current. So, in forward bias, to get a current, the condition is that whatever the battery you're putting, you're attaching the battery, that battery should be greater than the potential barrier. Once it is greater than the potential barrier, then only the majority carrier will move across the junction and thereby there will be a flow of current. Now, the depletion layer is reduced because the currents are flowing and there's a force from the both the sides, and thereby the depletion layer will reduce in this. In forward bias, the force in the depletion region is like push, so the depletion layer actually reduces, and therefore the junction offers a low resistance. So depletion layer acts as a resistance because there is a devoid of free charge, there is no charge carriers. So the depletion, lesser the depletion region, less will be the resistance. More the depletion region, more is the resistance. If the depletion region gets smaller, thereby the resistance gets smaller and thereby the flow of current increases. So the next topic is reverse bias. When a battery is connected across the junction diode with its negative terminal connected to the P side and the positive terminal is connected to the N side. So the N side is connected to positive terminal, P side is connected to negative terminal. The majority carriers are pulled away from the junction and thereby the depletion region thickness increases. The depletion region increases, thereby the resistance also increases. So no current flows through the majority carrier. A very small amount of current flows due to minority carrier. If reverse bias is continuously increased, then at a certain value, the covalent bonds breaks down and a large amount of electrons is released, thereby causing a abrupt increase in current, which is also called Zener voltage. So in reverse bias, what happens is that the N side is connected to the positive terminal, P side is connected to negative terminal, and the force that takes place acts on it is the pull. So the depletion layer increases, thereby the resistance also increases and the current flowing through it decreases, and it's found that no current flows through the majority carrier. Whatever the current is found to flow, that is due to the minority carrier. Now if I increase the reverse bias constantly, then a time will come, a certain value, what will happen, the all the covalent bonds, all the semiconductors, the silicon or the germanium's covalent bond, it will uh, it will break down, and thereby all of a sudden they will get a huge amount of current, which is known as the breakdown mechanism, and this is called the Zener voltage. At that time, what the voltage at which it occurs is known as Zener voltage. So there are two type of breakdown mechanism that we'll study now. One is avalanche breakdown, another is Zener breakdown. So in this breakdown, a huge amount of current is passed, but the change in the voltage, there is not much change in the voltage. That's why it is said that the diode behaves as a voltage regulator. It regulates the voltage. The current increases, but the voltage does not increase. So now we'll understand the graph for the forward bias and for the reverse bias. Now we all know this. In the forward bias, what we are doing is that we are connecting the p side with the positive terminal and the n side with the negative terminal, right? This is the forward bias. Now what we are doing, if we connect the diode with the biasing, we did the biasing p with the positive, n with the negative, and now I'm increasing the voltage. Now when I'm increasing the voltage, a small amount of current I will get. As you can see in the graph, when I increase a small amount of voltage, the current increase is also very small. But what happens for the silicon? For the silicon, what happens when it comes to near about 0.7 volt, then with a small change of the voltage, we are getting a huge amount of current. Clear? So when it is about 0.7 volt for the silicon, for germanium the value is 0.3. This is the value which I'm saying is the potential barrier or barrier potential, that is written in this thing. This is what potential barrier, it is the potential barrier which is developed when the p type and the n type is connected, and the potential barrier which it has itself. So the silicon has 0.7 and germanium has 0.3. Whenever, for example, if I take a silicon and I do this experiment, then what will I find that when the 0.7 volt come, from there onwards, that is the breakdown voltage. What happens over there is that with a small change in the voltage, a huge amount of current is seen, a huge amount of current is passed. So now we'll study the graph of the reverse bias. Now before studying the graph of the reverse bias, one thing you need to remember, whenever you're plotting a graph, for example for the forward biasing, what you will do with the forward current, the graph you're doing forward current and the forward bias. The forward biasing is for the voltage. In voltage, forward bias means only voltage, that will be in volt. Forward bias will be, or the it will be, the voltage will be in volts only. But the forward current, the unit for the forward current will be in milliampere, it in milliampere. But for the reverse current, when you're plotting for the reverse biasing, reverse bias versus reverse current, the unit for the reverse current will be micro, in micros, because in reverse the current is due to the minority carrier, whereas the forward current was due to the majority carrier. But so if we are getting in milliampere, that is, and this one in reverse one we are getting in micro. Next is that the same phenomenon does occur like this. When you are increasing the voltage, a small amount of current is found, but when breakdown occurs, what happens is that when breakdown occurs, when it is a breakdown, when we say breakdown occurs, means when there is a small change in voltage but the huge amount of current is found. The change of voltage is very small but the large amount of current is found due to the small change of voltage. That is called breakdown. Breakdown means only that all the covalent bonds or the huge amount of electrons are being produced. That's why it's called breakdown. Okay, so in this, when there are two type of breakdowns, one is avalanche breakdown, another is Zener breakdown. So what happens in the breakdown, both the characteristics are same. When the breakdown occurs, where there is a no much change in the voltage but there is a huge change in the current, right? Now in case of avalanche breakdown, the reverse voltage of the avalanche breakdown is greater, and the reverse voltage for the Zener breakdown, the breakdown which happens in the Zener breakdown, that is less compared to the avalanche breakdown. So the next we'll study the breakdown mechanism. There are two breakdown mechanism. One is avalanche breakdown and the other is Zener breakdown. Now, avalanche breakdown occurs in a PN junction diode. So what happens is that when the reverse voltage is increased, the electric field across the junction increases. Since the voltage is increasing, therefore the electric field will also increase. Then what will happen? The electrons will be accelerating at a higher energy, and thereby it will break the covalent bonds and more electrons will be produced, right? So what I'm doing, I'm increasing the reverse voltage, the electric field is increased, then the electrons are getting accelerated. Once the electrons get accelerated, it starts breaking the covalent bonds, and thereby what happens, the electrons are produced in a huge amount. This avalanche breakdown occurs when the width of the depletion region is large. Okay, and next is that in this case, what happens? The electrons that are knocked out by the collisions, they forms a reverse current. Okay, this mechanism is known as avalanche breakdown. In avalanche breakdown, it is a cumulative process, is a multiplication process, you can say. Like two bonds are there, two bonds break, the two electrons breaks one bond, becomes two, the two electrons again break two more bonds, it becomes 4, then 4 to 8, 8 to 16, and goes on. So it is known as a cumulative process. In this, the external source, that is the battery, is giving certain amount of energy, that is creating the field which is giving the energy to the electrons. The electrons breaks the bonds and the electrons are being generated, and these electrons forms the reverse current, right? So this is the process of avalanche breakdown. Okay, Zener breakdown. When the external field is very intense, the electric field directly causes the covalent bond to break and a large number of electron hole pair are produced. This causes a sudden rise in the current, and the Zener breakdown is not caused due to collision, it causes due to the direct rupture of the covalent bond. This happens when the width of the depletion layer is small. So what happens is that when there is an external field is given, the electric field is very strong over there, intense electric field. So what happens? It directly the bonds, the covalent bonds direct rupture. It happens that the covalent bond directly all break down all at the same time. It's not due to collision. The breakdown does not occur in the collision. What happens in the avalanche breakdown? Avalanche breakdown, the electrons are being produced by the collision. But over here in Zener breakdown, there is a direct rupture of the covalent bond due to the external field, due to a huge amount of or an intense amount of external field being applied, and thereby what happens? There is a direct rupture of the covalent bond. What happens to this? That the electrons and the hole pairs had been created. In this, the junction, there's a huge amount of current developed, and in this case, the depletion layer is very small. very small amount of, very small, the thickness is very small. So in Zener breakdown, it occurs in PN junction. It is highly doped, an external field is applied, and thereby all the covalent bonds directly rupture, or direct rupture takes place. The breakdown does not cause due to collision, and there is a huge amount of electron and holes are there, and this increases the sudden rise in the electric current. There's a huge amount of electric current. Rectification: the process of converting the alternating current or voltage into direct current or voltage is called rectification, and the device is called rectifier. And a PN junction or a diode can act as a rectifier. So act as a rectifier because it allows the current in one direction. So diode can be used as a rectifier. Types of rectifier: there are three types of rectifier. One is half wave rectifier, full wave rectifier, and bridge rectifier. So in this video we'll discuss two topics: half wave rectifier and full wave rectifier. So the next topic is half wave rectifier. Before understanding the half wave rectifier, we need to understand the principle of rectifier. When a PN junction is forward biased, the current flow through it and the resistance offered by it is very low. But when it is reverse bias, the junction offers a high resistance and almost no current flows through it. So when the PN junction diode is forward biased, the current will flow through it, and when the PN junction is reverse biased, the junction offers a high resistance and thereby no current will flow through it. Right? This is the principle of it. Now next is the, according to this principle only, the half wave rectifier and the full wave rectifier as well as the bridge rectifier depends on it. So forward bias means the current will flow through it, reverse bias will no current will flow through it. So in half wave rectifier we need a AC source, we need a transformer, we need a diode and the load resistance. We can do the circuit directly also, just by putting an AC source, the diode and the load resistance. No need of putting the transformer. But transformer is used due to certain things. There is a lot of advantage to it. First of is that if I put a transformer, what I can do it is that I can step up and step down. I can increase and decrease the current. Next is that I can also isolate, because of the transformer, the input circuit and the output circuit is isolated, and thereby if I can isolate the AC power line from the output circuit, so there is no chance of an electric shock. So if the back current flows also, there is no chance of getting the shock. So this is the advantage. That's why we use a transformer. There are many diagrams given in many books where the transformer is not been included, but it is better to always to have a transformer, because transformer increases, it can help in step up step down, and also number two is that you can say that it isolate the input power input circuit and the output circuit, and thereby there is no chance of getting electric shock. Now if you see the circuit over here, when an AC source and a diode is connected through a transformer and the load resistance, and when there's a positive cycle comes, when the positive cycle comes over here from the in the primary, and it induced to the secondary, and the diode gets positive terminal and the another end of the diode. So if you see the diagram, the P will get the positive and the N will get the negative, and thereby the diode will become a positive, and thereby in the positive cycle the current will flow through it. Whereas the same opposite thing will happen when it is in the negative cycle. So the P will get the negative and the N will get the positive. And thereby what will happen is that the according to the principle of the rectification or the rectifier, it is that if it is a reverse bias, no current will flow through it. So when the negative cycle passes through it, the diode becomes a reverse bias and thereby the no current flows through it. So the diode becomes reverse bias and thereby no current flows through it. And in this we can say, see, the AC is converted into DC. The output is now unidirectional. So this is how this works. The efficiency of a rectifier, for the half wave rectifier with an ideal diode, is only about 40.6%. So the efficiency comparing with an ideal diode is almost 40.6, which is very less. And why it is called half wave rectifier? Since it's only the half of the AC is rectifier, that's why it is called the half wave rectifier. So the next topic is full wave rectifier. A rectifier which rectifies both the halves of the AC input is called full wave rectifier. It also works in the same principle. It works on the principle that the junction diode offers a low resistance during forward bias and high resistance during reverse bias. Thereby, during forward bias, a large amount of current will flow through it, and during reverse bias, almost no current will flow through it. So, in this full wave rectifier, two diodes are connected in such a way that if one gets forward bias during first half cycle, the other will get reverse bias. But when the next opposite cycle will come, the first diode will get reverse biased and the second diode will get a forward bias. Okay, so in this full wave rectifier, a center tap full wave rectifier, a center tap is used. So as you can see in this diagram, there are two diodes, D1 and D2, right? And load resistance is also connected, and there is an AC cycle and a transformer. The transformer that has been taken is a center tap transformer. Now, the working of this full wave rectifier. Now, what happens is that during positive cycle, the terminal A, as you can see in the diagram, the terminal A becomes positive, thereby the D1 diode is forward bias, and the end B is negative, thereby D2, the diode 2, is reverse bias. Okay, so the current will flow through D1 and RL, right, as the direction is given also from D1 to RL. Next, during the negative half cycle, the D1 diode, the upper one, the D1 diode will be reverse bias, no current will flow through it, and the D2 diode, which is in the lower, will be forward bias and it will conduct current, and the current will flow through RL. So the direction through RL from this time is also same. Okay, thus the current will flow through RL in the same direction. If the diodes are ideal, if I take an ideal diode, the efficiency of the full wave rectifier will be about 81.2%, which is compared to the half wave rectifier, it's almost double. So this is the whole working of the full wave rectifier. So the last topic is Zener diode. The Zener diode is a properly doped PN junction diode which have a sharp breakdown voltage. It is always works in reverse bias. It works in breakdown region, so it is called a breakdown diode. The crystal is so doped that the characteristics beyond the breakdown is vertical. This means even though there is a large variation of current, the voltage remains constant. So it is used as a voltage stabilizer. So these are the characteristics of the Zener diode. So the last topic is the characteristics of the Zener diode, and we'll discuss the graph of the Zener diode. The Zener diode is properly doped such that it has a sharp breakdown region. If it is heavily doped, the depletion layer will be thin and the breakdown will occur at low voltage. So if it is heavily doped, the depletion layer will be thin and the breakdown will occur at low voltage. Whereas if it is lightly doped, the breakdown occurs at high voltage. Next is that the reverse voltage at which the breakdown occurs is called Zener voltage. The forward characteristics curve is same as that of an ordinary diode and the Zener diode. The difference is only in the reverse bias. What happens in the ordinary diode, the reverse bias, there is a one slanting line over there. Graph of the reverse bias will be slanting, but in the case of the Zener breakdown or the Zener diode, in the case of Zener diode, the breakdown will be very sharp. It's like a vertical line is there, means almost the voltage is constant, there is no change. Whereas in the ordinary diode or simple diode, where it is not particularly doped for the making it a Zener diode, it's a normal diode. In that, the voltage, there is the line of this is not vertical, it's a slanting line which shows that the voltage vary a little. Whereas in this case of a Zener diode, the graph, the line will be very much straight, that shows that the voltage is constant. That's why the Zener diode is used as a voltage stabilizer. Thank you.